Okay, without further ado, let me introduce our speaker, who I'm sure will be known to most of you, Professor Michele Dougherty. Just a few words about her background. Michele grew up in South Africa. She did her first degree and her PhD in South Africa. She then moved to Germany, where she was a postdoc for a couple of years, and then came to London, and she's been at Imperial College in South Kensington for more than 20 years now. And in fact, she told me earlier, though I had heard a rumour about this, that as of January next year, she'll be head of department of the physics department there. This is one of the largest and most prestigious physics departments in the country. Michele and I have known each other for many years now through the Cassini-Huygens project. We both worked together on this, and it's the last 6 months in particular of that project that Michele is going to talk about. She's one of the world's leading experts on magnetic fields in space and the measurement of them through spacecraft instrumentation. Now, I have to say that years ago we used to discuss or argue about this subject. I was not convinced that measuring magnetic fields was that useful, and I couldn't understand why we would be spending, £1 million a time on yet another magnetometer to fly on a spacecraft. I have to say, I have to grudgingly admit that over the years I have modified my views slightly, and I think you can now make a case for flying magnetic instruments. Anyway, I'm sure that Michele in the next 45 minutes will convince all of you that they're in fact the most important instruments to fly in a spacecraft. Anyway, Michele Dougherty.
Hello everybody, really nice to see you all. I've been told I have to stand in the middle and not pace, so I will try and do that. What I'm going to do today is talk to you about my involvement in Cassini, one of the discoveries that we made during the main part of the mission, and then I'll end by talking about the end of mission itself. I still have to pinch myself a little bit that it's actually over when you've been involved in something for as long as we were. John, of course, longer than me. His hair is much grayer than mine. You can't quite convince yourself that it's actually over, but it is. Now, this view here of Cassini is one of my favorite ones. This is made up of lots of different images that were taken by the camera on board Cassini, all put together to give you a view of the entire Saturn system. And you can see the sun is essentially behind Saturn. You can see it peeping around from behind the edge of the planet. You can see the rings in all of their glory. And you can see one of the other rings called the E ring, which is this rather diffuse ring here. And those of you with either good eyesight or sitting close to the front will see that you can see what look like plumes or bits of dust coming off the rings. And you can see it in quite a few different places. The reason you can see it in different places is because this image was put together over a period of time. It's essentially the same plume, but the moon that's generating it is orbiting around Saturn, and so that's why you can see it at different places. And that's one of the things I'm going to talk to you about. So it is a very large international project. These are all the different countries from which there were both engineers and scientists involved. Probably over the years, 3,000 to 4,000 people have been involved. This shows you a view of the spacecraft itself. This was the Huygens probe, which was the European Space Agency built part of the mission, and that's the probe that John had an instrument on, and it traveled down through the atmosphere of Titan and landed on the surface. This white umbrella thing is the high-gain antenna, and once a day the spacecraft would turn at the Earth for 8 hours and send data down via the high-gain antenna. And this here is the magnetometer boom. That's the boom that my instrument was placed on, and it actually consisted of two different instruments. One of them halfway down the boom, which was built at Imperial College, and one right at the end of the boom, which was built from the Jet Propulsion Lab in California. And in fact, life became very complicated for us as a team because a year after we reached Saturn, this instrument at the end of the boom stopped working. And so for us to be able to calibrate our instrument to work out where the zero level of the instrument was, we had to roll the entire spacecraft to do that. And that's not something that was planned, but it's something that we did on a routine basis. And in fact, we did it most importantly at the end of the mission phase as well. This is a view I always like to show because it gives you an idea about how large the spacecraft was. It was essentially 2 stories high. We've got people standing down. Oh, I pressed the wrong button, but luckily I was facing the wrong way. Planned, of course. You've got people standing here, so you can see how large the spacecraft is. And this was in the vacuum chamber, where the spacecraft and the instruments were tested before launch. We had to make sure that they could survive in the environment that they were going to be in, so in the vacuum of outer space. But also there was a very large temperature range that they needed to be able to operate in. At about 170 degrees Celsius when we flew past Venus, to about minus 100 degrees Celsius out at Saturn. So the instruments and the spacecraft needed to be able to survive that. One thing you will notice is in this view here, the boom is not visible, and that's because you can't launch a spacecraft with an 11-meter boom sticking off from the side of the spacecraft. And so what they did is they folded it away into that canister that you can see there. And when we flew past the Earth on one of the flybys we had, they deployed the boom. The gold stuff you can see is actually gold foil, which acts as a thermal blanket, and it helps keep the instruments and the spacecraft at a reasonable operating temperature. These are the 2 instruments. I'm not going to talk much about them at all, but this was built at Imperial College just up the road, and this was built at the Jet Propulsion Lab, and this is the one that unfortunately stopped working. So we essentially only had one working instrument for most of the time that we were at Saturn. This is a rather complex plot, but let me just quickly talk you through it. What we're doing is we're looking down on the north pole of the equatorial plane. We have the sun here. We have the different planets' orbits, so we've got the orbit of Jupiter here, we've got the orbit of Saturn here, and we've got the orbit of the Earth in here. You can't launch a spacecraft as large as Cassini with enough fuel to get it straight out to Saturn. And so what we did is we flew past other planets, and we called them gravity assist. It's a little bit like having a stationary billiard ball and a moving one. If the moving one bumps into the stationary one, it gives it the stationary one a bit of energy, and that gets it to move. And so if you fly close enough to a planet, you can gain a bit of energy from the gravitational well of that planet. And we flew past Venus twice, the Earth once, and then we flew past Jupiter, and we eventually got to Saturn in 2004. So after launch, it took us 6.5 years to get there. So you need lots of patience to be involved in outer planetary missions. So there were 4 main areas that we were going to focus on. We were going to try and understand Saturn and its internal structure and the rings and how they might have formed. We wanted to focus on Titan, and we did that by the Huygens probe traveling down through the atmosphere of Titan, but the Cassini spacecraft flew past Titan 160 times by the end of the mission. One thing I didn't say is that Titan is the only moon in the solar system that has a very dense atmosphere, very similar, we think, to what the Earth's atmosphere was like when it first formed. And that was one of the reasons we wanted to go to Titan, because it's almost like seeing a snapshot in time. You can have a look at Titan's atmosphere and start getting an understanding about how our atmosphere might have evolved. Bottom left is a view of one of the moons, which is called Enceladus. We had numerous flybys past these moons planned. And then last but not least is the environment around Saturn, the magnetic field of Saturn protects the environment from the effects of the sun. And to be able to understand an environment like this, you need to spend time there, and that's why an orbiting spacecraft is so good. I'm not going to have time to talk about everything, so I'm going to focus on the discovery we made at Enceladus, and then I'm going to focus on the end of the mission and the orbits that we planned so we could try and understand how long a day on Saturn is. It's a bit embarrassing, but we still don't know how long a day on Saturn. I keep being asked when we will know, and I keep saying give us a few months. I never specify which month, but we're getting there, I think, and I'll describe that to you in a bit. So, John has seen the slides, and he now understands why magnetometers are so important. But from my perspective, you need to understand the magnetic field in an environment to understand how the environment behaves. And you can't see a magnetic field. If you could, this is what it would look like. So we've got a magnetic field generated in the interior of the Earth. It's a dipole, essentially. And if you could see the magnetic field lines, it would be these red lines here, these lines of force. One way of thinking about it is if you had a piece of paper, you put a bar magnet underneath the piece of paper and iron filings on top of the paper, the iron filings would lie along the lines of force of the magnet, which is essentially what you're seeing here. Now, when a planet rotates on its axis, those magnetic field lines rotate as well. And so if you're a moon somewhere out here, the magnetic field lines of the planet are going to move past you, and they're going to rotate at the same rate as the planet does. And that's something you'll need to keep in mind as I show you some of the data. Okay, so let's talk a bit about Enceladus. Enceladus is pretty small. Its diameter is 500 kilometers. This is a view which was taken by the camera on board Cassini. It was 2 different images put together. And what you can see is there's some cracks, some very deep cracks on the surface, but there are not many craters. And that was a real surprise because there's a moon quite close by to Enceladus called Mimas, which is also orbiting around Saturn, whose surface is covered in lots and lots of craters. And so the implication was that something else is happening at Enceladus. Maybe something is resurfacing it to make it look as young as it does. One of the things that we knew or we postulated about before we got to Enceladus with Cassini is that diffuse E-ring that I showed you in the first image is made up, we thought, mainly of water ice. The surface of Enceladus from the Voyager and the Pioneer spacecraft is made up mainly of water ice. And so people have always wondered, could Enceladus somehow be the source of E-ring? But no one understood how that could be. Now we had, in early 2005, we had 3 flybys of Enceladus planned. One in February, which was just under 1,300 kilometers above the surface. A second one a month later, which was 500 kilometers away. And the third one was going to be in July, and it was going to be about 1,000 kilometers away. But based on the data that we took on the first 2 flybys, we were able to persuade the Cassini project to take us much closer on the third flyby because we thought we were seeing something rather interesting. And I'll talk you through what it is we thought we were seeing. So this gives you an understanding of where Enceladus is. So we've got Saturn, of course, off to the left with all of the visible rings that you can clearly see. Mimas is orbiting at this distance away from Saturn, and that's the moon that's covered in craters. Enceladus is orbiting just under 5 planetary radii away from Saturn, and the inner edge of the E-ring starts quite close to the orbit of Enceladus, and it actually extends way out into the distance. Titan is somewhere over here, if we're looking at that view. But I think one of the main points here is that the particles in the rings are made up mainly of water ice, and we've always wondered where they came from. So you have to be a magnetometer person to get excited by mag data. I've tried with John, and he's just not interested. But I just want to show you what we were able to do. This is a day's worth of data. This is 24 hours worth of data. This is the data from the first flyby of Enceladus back in February 2005. And the way that you measure the magnetic field, it's a vector. Oh, I'm pacing. I've got to stand still, sorry. You measure the magnetic field as a vector. So you measure the 3 components of the magnetic field. So the radial component, the north-south component, the azimuthal component, which is the one that goes around the planet, and then the magnitude at the bottom here. And you can see, if you've got good eyesight, that there's a pimple in the data just there, and just there as well. And this data here looks as if it was supposed to be doing that, but something happened. And similarly, this data was following that curve, and something strange happened there. That was the flyby of Enceladus. So what we did is we subtracted the magnetic field of Saturn away from the data to see what we could see. And what we're doing now is we're looking down on the north pole of Enceladus. Saturn is off to the top. The magnetic field and the plasma from Saturn are coming from this direction here. And this is the trajectory of the spacecraft. And overlain on that trajectory are the magnetic field vectors that are left after we subtracted the influence of Saturn away. And it looks as if they're pointing towards Enceladus, and then suddenly they're not allowed to. Something is stopping them from pointing down and penetrating down onto the surface. So it's almost as if Enceladus was a much bigger obstacle to the flow of plasma and magnetic field coming from Saturn than it looks. The other thing that we found is that there was a very large increase in wave activity. Let me go back. If you have a look here, there's a lot of noise in the data. There, you can see it quite clearly here as well. And that noise is actually activity that you can measure, and you can work out what molecules are generating that noise. And what we found is that there was a sudden increase of water group ions as we got close to Enceladus. So what we did is we put together this little movie to show what we thought was going on. So we're looking at it from two different viewpoints. The first one is, there we are, looking down on the North Pole of Saturn. So there's the North Pole of Saturn. We've got the rings of Saturn shown by those circles there. The blue lines are the magnetic field lines of Saturn that are rotating around with Saturn as it rotates on its axis. And the little orange ball is Enceladus. If Enceladus was a dead body, the blue lines wouldn't see it. They'd move straight through it. But what we seem to be seeing, and now we're looking sideways on, here the blue field lines of Saturn. If Enceladus was dead, it wouldn't see Enceladus, and the field lines would just move straight through. But instead, what we seem to be seeing is that the magnetic field lines were being held upstream. Something was stopping them penetrating down onto the surface. And one way that you can do that is if you have an atmosphere, just like we have on the Earth. The upper regions of the atmosphere become ionized by solar radiation, and those ions stop the magnetic field from being able to penetrate through. So what we did is, because there are more people other than John who don't understand mag data. I'm sorry, John, it's the last time I will refer to your... No, I can't. We thought it would help to show what we thought was going on. So this is a schematic that we put together, which essentially shows the field lines of Saturn, shows Saturn itself. The plasma and the field lines of Saturn are moving towards Enceladus. And we said what we thought we were seeing is an atmosphere covering the entire surface of Enceladus, which was stopping the field lines getting down onto the surface. Now, this was a real surprise because Enceladus is small, 500 kilometers in diameter. We saw it on two separate flybys, a month apart, which meant that if there was an atmosphere, it was being produced all the time. Because the gravitational field of Enceladus is quite low, you would have expected the atmosphere to be lost if it wasn't being produced all the time. So what I did is I went out to the Jet Propulsion Lab and I gave a presentation. I showed them this, I showed them the data. And I said we thought we were seeing an atmosphere. We weren't sure, but we thought it was exciting enough that we should try and make the third flyby 3 months later go much closer to the surface. Now, this was always something that we had worried about. We had spent the 6.5 years it took us to get to Saturn planning the first 4 years' worth of observations. And people had asked, what happens if we make a discovery? Can we change the orbit? And the project had always told us we could, but this was the first test as to whether we could. So they agreed, and instead of being 1,000 kilometers above the surface, it was 173. And I gave it away. And fortuitously, the spacecraft came up from below, and it was going to fly below the south pole of Enceladus. And when we did that, and I must confess, I didn't sleep for a couple of nights before this flyby, because if we had seen nothing, no one would ever have believed me again, and no one would ever have thought magnetometers were important. But what we found was, instead of it covering the entire surface, it was almost like a cometary plume, a jet of water vapor coming off from the South Pole. It was just focused at the South Pole. But because we went so close, most of the other instruments on the spacecraft were able to take data as well, and I'm going to show you some of that data. So this is two different data sets. The first one is in the top left, and that's from the imaging camera on board. And what I want to point out is not only the youthful surface that you can see, and there are some craters, but it's these cracks at the South Pole, which the imaging team called tiger stripes. Now, there's another instrument on board the spacecraft which is able to remotely measure the temperature of a body. And this instrument expected the surface to be hottest at the equator because that's where the solar radiation is strongest. And what they found was, yes, there was a hot region at the equator, but there was a real hot spot right at the South Pole. Now, when I say hot, we're talking relative terms here. We're at a minus 100 degrees Celsius, but out at Saturn, which is 10 astronomical units away, that's pretty warm. And so what we did, or what those teams did, is we overlaid this temperature map on top of the image, and you can see that the hottest spot, a whole 91 degrees Kelvin, was lying over one of the tiger stripes. And so that meant that there were these cracks on the surface where internal heat was leaking out of the surface, water vapor was leaking out as well. And so the implication is that something is going on at Enceladus which is keeping the interior warm. You would have thought a moon of this size would have long cooled down from when it first formed, but there's something clearly going on at Enceladus which is making the water ice in the interior into a liquid, and this is then leaking out in the form of water vapor. This is a view which was taken by the camera looking back at Enceladus on one of the subsequent flybys, and you can clearly see the very fine structure in the plume. The different colors show you the different densities, and you can also start seeing the fact that there are different sources. There's a source there, and there's a source there as well. And so you have this water vapor and dust coming out of the plumes, but they seem to be opening and closing depending upon where Enceladus is in its orbit around Saturn. So we think tidal forces are opening and closing these different cracks. Now, based on these observations, we then, the original plan for Cassini was it was going to orbit around Saturn for 4 years, and so it was due to end in 2008. But the data we were getting was so spectacular, the instruments were working as well as they were, that they continued to extend the lifetime of the mission. And for most of those extensions, Enceladus was one of the focuses because we really wanted to try and understand it better. Particularly once we realized that not only was there water vapor and dust leaking out of these cracks, but there was organic material leaking out as well. It's a couple of slides away. I've jumped a bit ahead of myself, sorry. This goes back to the statement I made a little bit earlier about there being different sources. These stars here, this is a view looking at the South Pole. We have the heat emanating from the interior, which is being projected onto that view. This is 50 kilometers, that distance there, just to give you an understanding about the size. And these stars here show you the different sources, and these sources are opening and closing depending upon where you are in the orbit. This is the one I started talking about earlier. This is an instrument known as the ion neutral mass spectrometer, and what this instrument does, it essentially tastes what it's flying through. And so on one of the close flybys, I think the closest flyby we had was 25 kilometers above the surface, the project said they'd never do that again because the mag boom caused the spacecraft to begin to wobble a bit. And if you enter a really dense atmosphere, that's what you would expect. That's one of the reasons at Titan we never went closer than 950 kilometers to the surface because the mag boom would have made the spacecraft unstable. But in one of the close flybys through the plume, this is what we found. Methane, lots of water vapor, but we knew that because we had seen that in our data. Simple organic material and complex organic material, and also carbon monoxide and carbon dioxide as well. And in fact, on a later flyby, I didn't add it to this slide, we found ammonia in the plume. And ammonia acts as an antifreeze at those kind of distances. And so that might be one of the reasons why we're able to have liquid water out at these very large distances, because it helps to keep it liquid at temperatures that you wouldn't expect it to be possible. And so Enceladus is now one of the places in the solar system where life might potentially form. You need 4 things for life to be able to form. You need a heat source, which we have at Enceladus. You need liquid water, which you have. You need organic material, which we've got. The 4th thing you need is for those first 3 things to be stable over time so that something could happen. And that we're not sure about. But there are plans to send future missions to Enceladus. It's difficult, though. If we wanted to go into orbit around Enceladus, you need a huge amount of fuel to be able to do that, because its gravitational field is so small. You can't really use Enceladus to get into orbit, so you would need to fire a spacecraft engine for quite a long time to be able to do that. I want to talk for 2 slides about Jupiter, partly because what we discovered at Enceladus, I think, enabled the plan that we have to go to Jupiter to come to fruition earlier than it might have done. The focus on icy moons in the outer solar system having liquid water under their surfaces and organic material allowed us to make the case that the next big planetary mission that we want to do is to go to Jupiter. And this is actually one which is being built and run by the European Space Agency. I have a magnetometer instrument on this spacecraft as well. And what the plan with JUICE is, and I've got a slide after this which describes JUICE a bit, is, we're going to focus on 3 of the 4 large moons. We're going to focus on Europa, which we know has a liquid water ocean under the surface. We're going to focus on Callisto, which also has liquid, but it's really strange. It's not differentiated. Its interior structure is very different to the other moons. And then we're actually going to go into orbit around Ganymede. For a magnetometer person, Ganymede is a dream. It's got its own planetary dynamo field. It's the only moon in the solar system that does. But in addition to that, it's got liquid underneath the surface. And what we can use my instrument to do is we can actually measure the electrical currents that are flowing in that ocean. And you can work out from those signals how deep the ocean is and how salty it is, what the salt content is. Now, I think the next slide, yes, that shows just an overview of JUICE. It shows Ganymede in the background. It shows an artist impression of the spacecraft, but that's pretty close, actually. We're not using radioisotopes to fuel JUICE. We're using solar panels, and so we have these vast solar panels on either side of the spacecraft. We're building the engineering model of our instrument at the moment. What happens is we build 5 or 6 models until they're good enough, and then we have the final model that we fly. The plan is we will launch in 2022. We will get to Jupiter in 2030. I won't tell you how old I'll be. And we'll orbit for 3 years. But I'm making sure I've got lots of young people on my team so that if we stay there for 20 years like we did with Cassini, we'll still have someone who can actually work with the data. Okay, so let me go back to Cassini now. And in the last 15 minutes or so, what I want to do is I want to focus on the last 6 months of the mission, which culminated in the spacecraft burning up in Saturn's atmosphere on the 15th of September. Now, this just gives you an understanding of what these orbits look like. So we've got Saturn here. The Earth is way off to the top left. This is the orbit of Titan over here. And there were 2 phases to the end of mission. Now, what we wanted to do is Cassini was running out of fuel. So we were going to lose control of it at some stage. We didn't want it to crash land on Enceladus, where there might be the potential for life. We didn't want it to crash land on Titan, where there's liquid ethane and methane on the surface, potentially life in some form as well. So what we decided to do is we would burn it up in the atmosphere of Saturn. But before we did that, we wanted to get as much data out as we could. So we planned these end-of-mission orbits. There were, as I said, 2 phases to it. The first phase was they were the ring-grazing orbits, or the F-ring orbits, where the closest approach to Saturn was just beyond the edge of the F-ring. And we then used Titan, and we were in those orbits for about 6 months. And we then used Titan as a final gravity assist to get us to change the inclination, and we then moved on to these blue orbits, or the grand finale orbits, which were in the gap between the rings. We used data from these orbits to better constrain the kind of measurements we were going to make so that we could focus in on what we wanted to do at the end. Now, these end-of-mission orbits were designed with the magnetometer instrument and the gravity instrument in mind in particular, because one of the real surprises about Saturn is we don't know how long its day is. It's about 10.5 hours. And we don't know how its magnetic field is generated. One of our understandings prior to Saturn was that the way in which a magnetic field is generated in the interior is via a process known as the planetary dynamo. And we've always thought if a planetary dynamo is generating the magnetic field, the rotation axis of the planet and the magnetic axis of the planet need to have a tilt between them. 10 degrees, 5 degrees, it doesn't really matter. But if you don't have a tilt, we didn't think you could generate the field. At Saturn, we can't find a tilt. And so we thought if we got inside of the rings on these orbits here, we would finally find a tilt. Not yet, we're working on it. It's complicated because there are lots of different things going on, so we're trying to be very patient. I'm not renowned for my patience, but we're trying to be really patient and go through all the other things it could be before we get to the answer. This just shows you how close we got. We're essentially skimming above the cloud tops. The orange orbit is the final one, the one that put the spacecraft onto its burn-up trajectory in the atmosphere. Now, I've alluded to the planetary dynamo. This is one of the things that we were trying to find out with the end of mission orbits, is that, you know, these field lines that we measure outside are generated inside the planet. And by being able to understand how they're generated, it almost allows you to see inside the planet and get an understanding about the different processes taking place. We think it's generated by a planetary dynamo. You need an overturning convective motion. You need rotation to be taking place. And all of those things should give you a tilt, but at Saturn they don't seem to be. What we think is happening is that there is a small rocky core in the center, and then there's the dynamo region, which we think at Saturn is made up of fluid metallic hydrogen. We know that Saturn's mainly hydrogen. One way in which to get currents to flow is if you strip an electron off the hydrogen, you can make it metallic and you can allow currents to flow. And that's where we think the currents are actually flowing. But with the observations we made in the last 6 months, we will be able to resolve this. It's just we're being really careful. We need to take our time. This is a view which shows you what the spacecraft looked like on the first close orbit. We weren't quite sure what we were going to find in this gap in the rings. We didn't know if there'd be energetic dust particles. We didn't know if the spacecraft was going to be damaged. And so what we did is we flew with the high-gain antenna pointing in the direction of travel so that the spacecraft and the instruments behind it were protected. That was all very well. My instrument was sitting here. So I bit my nails. At the first orbit, we went out to the Jet Propulsion Lab, and I had nicely painted nails, and by the end of it, they looked an absolute wreck. But it survived, and in fact, it survived for all 22. And this was spectacular. We'd never designed the spacecraft or the instruments to do this. And the fact that it did is a testament to how carefully one builds instruments and how well the project at JPL looked after the spacecraft. You know, it was really interesting talking to Julie Webster. I'll show you a picture of her in one of the final slides. She was responsible for the spacecraft in the last 6 years of the mission. And she said it's like learning to drive a new car. To begin with, you don't push it too hard because you don't know how it's going to react if you go around a corner quickly. But as you learn what the spacecraft is capable of, you know you can push it really hard. And in fact, I pushed Julie quite hard because for the end of mission for us, when we're really close to the planet, we were in a measuring range of the instrument that we hadn't been in since we flew past the Earth 18 years ago. And so we needed to calibrate it as if it was a new instrument. And to do that, we needed to roll the spacecraft around closest approach. And when I first approached Julie, she said, "Hell no, I'm not doing that to my spacecraft." So I took her out to dinner a few times, used bribery and corruption. But, you know, she was always driven by the science, but she knew she needed to keep the spacecraft safe. I don't think I could have convinced her if it hadn't been for the fact that we were in the final phase of the mission. So this is the resting place of Cassini. This is a view that was taken by the visual infrared mapping spectrometer on board Cassini. And in fact, this was taken 12 hours before the end because Cassini was, of course, orbiting underneath the spacecraft. And so they worked out afterwards that this is where Cassini burnt up. And in fact, giving a more global picture, that's essentially where it burnt up in the atmosphere. For me, the most poignant moment, I think, was we were watching the signal coming back from the spacecraft, and it was essentially a flat line, and there was a peak in the data, and as long as that peak was there, it meant the spacecraft was talking to us. And the peak disappeared, and then it came back again, and then it disappeared for a final time. And that coming back again was the spacecraft trying to make sure it continued to talk. It hadn't been told it was burning up. And so it moved itself so that it could continue to talk for as long as possible. And we actually got one of the final bits of data, and that data is going to be really important to try and understand what we're seeing. So I think we're about to, no. That's a picture of Julie Webster. She was the one who said, hell no, when I asked her if we could roll the spacecraft. But this was just after the end of the mission. You know, it was almost as if we were grieving. It sounds awful. It sounds weird, but, you know, it was an instrument. But it took me a while to come to terms with the fact that I didn't have to wake up at 2 o'clock in the morning and worry if the instrument was okay. I knew it wasn't. You know? Okay, so now I think we're going to play a movie which NASA put together. I think the lights are going to go down a bit as well. But it essentially takes you through some of the highlights and what the plans were for the end of the mission. And everything we planned went perfectly. It was beautiful.
A lone explorer on a mission to reveal the grandeur of Saturn, its rings and moons. After 20 years in space, NASA's Cassini spacecraft is running out of fuel. And so, to protect moons of Saturn that could have conditions suitable for life, a spectacular end has been planned for this long-lived traveler from Earth.
5, 4, 3, 2, 1, and liftoff of the Cassini spacecraft on a 1,000,000-mile trek to Saturn. We have cleared the tower. Its program is in. Its program is in.
In 2004, following a 7-year journey through the solar system, Cassini arrived at Saturn.
The SOI burn attitude or pointing position and light up the rockets.
The spacecraft carried a passenger, the European Huygens probe, the first human-made object to land on a world in the distant outer solar system.
Huygens arrival on Saturn's moon Titan.
For over a decade, Cassini has shared the wonders of Saturn and its family of icy moons, taking us to astounding worlds where methane rivers run to a methane sea, where jets of ice and gas are blasting material into space from a liquid water ocean that might harbor the ingredients for life. And Saturn, a giant world ruled by raging storms and delicate harmonies of gravity. Now, Cassini has one last daring assignment. Cassini's grand finale is a brand new adventure. 22 dives through the space between Saturn and its rings. As it repeatedly braves this unexplored region, Cassini seeks new insights about the origins of the rings and the nature of the planet's interior, closer to Saturn than ever before. On the final orbit, Cassini will plunge into Saturn, fighting to keep its antenna pointed at Earth as it transmits its farewell. In the skies of Saturn, the journey ends, as Cassini becomes part of the planet itself.
very much.
Thank you so much, Michele. Fascinating presentation, and every time I have a lump in my throat
I know,
when I hear
that's
it.
why I asked them to turn the lights down, so I could do it in private, you know.
Anyway, you behave very well with timekeeping, so we have
I know.
quite a bit of time for questions, if there are any. Okay, so wait for the microphone. Thank you.
Thank you so much. I'm not a scientist, but I love that. The organic materials, such as is on Enceladus, have we got any idea how it came to be there?
No. Probably from when the bodies first formed. They were probably left over from the original formation. Or something landed on it. A comet might have crashed onto the surface. We're still not quite sure how water came to the Earth, because didn't Rosetta show it was different kind of deuterium compared to...
D2H, right?
Yeah.
Yeah.
So, don't know.
Which is why we need a mission to go.
Absolutely.
Especially to Enceladus,
Absolutely.
yes.
Have we any idea of the sort of volume of water that's being lost by Enceladus, and has this been happening for millennia, or is it a relatively recent thing that's happening, do you think?
It's been happening. The answer about the volume is no. I can't think of them. I'm sure people have put some numbers together, but it's been happening since the 1800s, because that was when the first Earth-based observations of something strange happening around the rings of Saturn were made. People thought it was a problem with the Earth-based instruments. But so it's been happening since the 1800s. How long it will continue to go on, don't know. Sorry, that's the second answer I've said I don't know to. Please ask me something I do know so I don't look as if...
In the mass spec of the plumes,
Yes.
you've got several bars for methane and several bars for water. This is presumably isotopic distribution?
Yes, yes.
Is this the same as that on Earth?
The question was, is the isotopic distribution of methane and some of the materials the same as the Earth? I don't think it's exactly the same, but there is some overlap. Yeah. Hunter Waite is the person responsible for that. So if you did a search for a Waite paper, W-A-I-T-E, there's been some work that he's published on this, but it's not exactly the same as what we see on the Earth. Yeah.
My question concerns the first picture you put up
Yes.
at the beginning of your talk. I wonder if we could have it up now.
I have no control.
Oh.
Could we have the very first slide, if possible? I see some movement up there.
Okay.
So,
You see,
oh,
John's much more important here.
Is that the one?
It shows Saturn and its rings.
Yes.
But on the near side of the planet, there are bands which look as if they're extensions of the rings themselves.
Yeah, it's the shadow of
but
the
there
rings.
are discontinuity between it and the rings outside the picture of a...
It's the shadow of the
So-
rings.
It's a shadow effect.
It's the shadow of the rings, yeah. So that's why it's not quite continuous, because, yeah.
I'm going to ask a question, if I may, and this is slightly left field, but so don't answer it if you don't want to. But you mentioned, for example, Julie Webster, and you showed
Yes.
a picture of her. She was the spacecraft
Spacecraft manager.
manager
Yes.
for the whole project,
Yes.
I think.
Yes.
And, I mean, I know that at the end of the project scientist was Linda Spilker.
Yep.
Yourself were the PI of one of the big instruments. The camera, the PI was Carolyn Porco. So you can see where I'm going. There are quite a few women involved. I mean, it hasn't always been the case, and that, you know, that women were well represented in space research. I mean, certainly in the early days, wasn't the case at all. I just wonder if you have any comments about the role of women, and whether, I mean, because still the majority of the teams were led by blokes.
Yeah, they were led by blokes, but, you know, a woman came in and took over, so that was fine. I think we will have this problem solved when people stop counting. I'm not saying you're counting, but when people stop counting how many women there are in a team. I have never felt impacted by being female, but maybe that's because I'm a bit cranky and I say it as it is. I don't know. But I do know people who have been impacted quite badly. One of the things I really enjoy is at Imperial College, they're now 25% females in our undergraduate year. When I first arrived, there were 5%. So it's changing, slowly over time. But I wasn't impacted. I was very lucky.
Thank you, Professor Dougherty, for a very good talk.
Thank you.
I'm going to try and take you back to magnetic fields.
Okay. John might have to close his ears, but...
So you made your discovery because of the effect of the atmosphere on the magnetic field.
Yes.
I'd like to know if the magnetic field has an impact on the atmosphere, if it is responsible for driving the ionized atmosphere into the rather diffuse E-ring, perhaps.
It changes the way the ions... So it's not the atmosphere itself that's acting as the barrier, it's the upper region that's ionized. So it's the ionosphere that's acting as a barrier. And the magnetic field will change how the ions behave in the upper regions of the atmosphere. And of course, that will then impact further down.
But can it have a tidal force?
I don't think it will. When,
so thin.
Yeah, because, you know, if it was a very dense atmosphere, it might, but because it's just focused at the South Pole, I don't think it will. When I was talking about tidal forces, I was talking about internal gravitational tidal forces.
Yeah, one of the pictures shows the polar region of Saturn there with the hexagonal shape.
Yes.
Is that any relationship to the magnetic fields, or is
No.
do we not know?
I'd like to pretend that the magnetometer is the most important to understand everything, but no, we couldn't tell you anything about the hexagon.
Let me also make a comment and maybe ask a question, but you showed a picture of or an image of the magnetometer, or the two magnetometers.
Yep.
And I don't know if anybody picked up how old-fashioned they looked. Yeah. And I mean, it's important to realize that Cassini-Huygens was selected by NASA and ESA in, I think, 1990.
I was only about 2, you know.
So the design of the instruments was done over the next few years.
Yeah.
And because we design instruments for space relatively conservatively, you use slightly old technology because it's well tried and tested.
Absolutely.
So this is really the technology of the 1980s, isn't it?
And yeah, you aren't allowed to fly instruments on large missions like this unless they're at a technology readiness level of 9, which means you've flown them before. It can be in orbit around the Earth or in a balloon in the Earth's atmosphere, but you need to show that they've flown before. But also it helps if you show that they can survive the environment that you're going to be in. Because if you think about it, you don't want to send an instrument out there. It takes 80 minutes to send a command to Saturn. You know, that's how long it takes to get there. You need to know that it's going to work. And so you need redundancy upon redundancy. We lost one of our first bits of redundancy right at the start, but luckily the instrument built at Imperial was fine. I don't need to touch wood anymore, do I?
Okay, just to follow on, if it was so, you know, old technology, well tried and tested, why did it cost £2 million? You don't have to answer that. Right.
But I'm going to, because the bits that you put onto it, some of the sort of individual parts cost £500,000 each. You know, they need to be able to survive in the environment of space. John always badmouths the fact it takes £2 million to build a magnetometer. I'm not going to ask him how much it cost to build his little probe. How much did it cost, by the way?
The whole, we built a whole probe for, I think, 250, 300 million.
Yeah, but yours
For the
only
whole probe,
But yours only had to survive for a short period of time. You see.
That's true, 2 hours and 27 minutes.
John and I know each other quite well. That's why we're so lean.
But it is sitting there.
It is.
Whereas yours is mere
Burnt up.
gas and dust.
I know.
Okay.
But is it doing anything useful there?
Touche.
I'll stop. Yes.
Thank you for incredible lecture.
Thank you.
I'm curious how it looks like from a team point of view. A mission like that takes years. And I understand that the data is streamed constantly.
Yes.
Yes.
Well, 8 hours out of every 24. Yeah.
And is it managed all 24/7, 300? Yes, all the time by someone sitting there and the steer and actually.
There was always someone at JPL keeping an eye on the spacecraft, but because of cell phones now, they could actually go home and they'd be phoned straight away.
The aircraft is at some point automated.
Yes.
And then okay.
Yeah. What we'd do is we'd upload the commands to the spacecraft and leave it to it, and we would only interject if something went wrong, and it only went wrong a couple of times.
Then you only analyze data and perhaps you got the data and analyze it somewhere else, or
we used to get the data in our lab at Imperial. It would go to JPL and then come straight to us, and we would have to calibrate it, we would have to process it, and then we would give it to our team to work on. But we also had to put commands together to change what the instrument was doing. So we had 2.5 people working full time on operating the instrument, and that was just one instrument. So.
Thank you.
And it's worth adding, I think, that all of this data, whether it's from the NASA probe or the ESA probe, after a certain length of time, it is made available to the whole scientific community worldwide, isn't it?
That's right. We put it onto, it's called the Planetary Data System, so anyone can go onto it and access the data.
And it means that this data will be used, analysed, papers will be published for 20 or more years. In fact, until we have the next mission.
Absolutely.
Probably.
And in fact, while we were preparing for Cassini, once Cassini was launched and we were planning the observations we were going to make, we went back to the previous spacecraft data sets, Pioneer and Voyager, and we found stuff in the data that no one had seen. So you need new eyes on it. I mean, I hope we've creamed off the best of the discoveries, but I wouldn't be surprised if they find some really exciting stuff in the data.
Yes, thank you very much for recounting this extraordinary thing, which is the mission. But there is one problem that I have with something you said, which was that you had to burn up Cassini because it might have some negative impact on life formation on, amongst other places, Titan.
Yes.
But you landed Huygens on Titan.
But
so what was the difference between the two?
Yes. I should have been clearer. Huygens went through a planetary protection regime where, before it was launched, it went through all these procedures which cleansed it completely of any man-made germs, whereas Cassini didn't.
Thank you.
And so, you know, there are some people in the world who don't believe that we've had anyone walk on the surface of the moon. So we've got to be really careful that those people aren't given any ammunition if we ever find life on Titan or Enceladus. And they say, oh, yeah, but Cassini crash landed. So that was why. But yes, I didn't make it clear. Yeah.
About Enceladus, what's the latest thinking about the heat source, the internal heat source? And if I can slip in a second question, you showed the E-ring and you showed that there's a plume coming out. Is that... First of all, is the E-ring the Enceladus atmosphere, the outgassing? And is that plume associated with the South Polar outgassing?
The plumes that you could see in here are, but the reason you can see lots of them is this is lots of images put together. So it was where you can see the plumes, you can't see it very, but you know, there's a plume there. That meant when that part of the image was taken, Enceladus was there. So what's happening is that Enceladus is orbiting at the inner edge of the E-ring, and you can see the plumes coming out, but it's the material from the plumes are being picked up by the magnetic field, and they get put into a disk around Saturn.
The plume is the same.
So the material in the plume is exactly the same as the material in the E-ring. If you have a look at spectra of the two, they're exactly the same. As far as the heat source, we think it's originally tidal. We think the orbit of Enceladus was slightly more elliptical than it used to be, and so when it was closer to Saturn, the tidal forces were stronger, and that keeps the interior warm. But we think tidal forces are still playing a role because the cracks are opening and closing depending on where in its orbit around Saturn it is. So we think it's tidal.
Yeah, I mean, to pick up on the earlier comment about how long this has been going on, it's been observed since 1800s.
Yes.
The resurfacing must put that clock back billions of years, doesn't it?
Yes, I would think so. Yeah. There's one here.
Oh, yes. Over here.
In the last part of the film, when it was breaking up,
yes.
I wondered whether parts of it might actually bounce off rather than be pulled in by the gravity. Or do you think it would just all burn? And even when things burn, there's something left.
Yeah, I think it would probably fall in. Even if a bit broke off, it would eventually fall in because it is an atmosphere, so it has a density. And even if it made it through 1,000 kilometers, the pressure would get really high.
Yes, I was thinking before it fell in,
Yes.
would any of it bounce off the...
Yes, I think John's right. You would have to have been at a glancing angle. So, you know, even if a bit falls off, it's still on the same trajectory as the spacecraft was.
Going in.
So we wanted to make sure it went in, because we'd run out of fuel. We couldn't afford to bounce off. And in fact, we were on the fumes at the end. We really were. There was nothing left at all.
Thank you. And thank you for a lovely lecture.
Thank you.
I'm just going to make I think there are two questions at the back.
There's a lady at the back there as well.
I'll just make a comment about magnetometers, and I was reminded, you know, apart from this horrible 11-meter long boom, which is, you know, makes a spacecraft quite difficult to control, I'm reminded, a dreadful memory, that, of course, another implication is that you don't want to go halfway across the solar system and just measure the magnetic field produced by the other instruments on the spacecraft. So it imposes an incredibly tight regime of magnetic cleanliness. So that's why most instruments hate magnetometers, because you have to design your own instrument to be magnetically clean. And you know, at a very, very sensitive level. So it's very tough.
So I learned very early on to get a thick skin. I had to deal with people like John all the time.
Why is it so difficult to measure the length of Saturn's day? And is it the same for other planets, or is it just Saturn?
Thank you. And I should have pointed that out. The reason it's so difficult at Saturn is because the two axes lie on top of each other. On the Earth, it's easy. You can watch a solid part of the Earth move underneath you, and 24 hours later it comes back. On Jupiter and Saturn, it's much harder because you don't have a solid surface. It's a gas. And so there isn't one spot. Even the red spot is moving around. And so what you do is you use the fact that there's a tilt between the rotation axis and the dipole axis. You use the magnetic field as a result of that and radio wave data to measure. It's almost like a strobe light at Jupiter, once every day, which is 9.6 hours, I think. On Saturn, there isn't a tilt. And so when we look at the magnetic field, we got all excited when we first arrived. We saw there was a wave in the data, and we thought, that's the rotation. But depending on where you look, if you're looking in the northern hemisphere or in the southern hemisphere, it's different, and it changes with season. And so the implication is we're not seeing the internal rotation wave. We're seeing something that's going on in the atmosphere. And we need to subtract that away from the data to be able to get to the interior. We thought by going inside of the rings, it would disappear, and it doesn't. And so that's why it's so hard for us to work it out. We will get there, she says, hopefully.
In a few months.
In a few months.
Okay, well, the clock has finally caught up with us. It's been a fascinating talk, and you can see how much interest it's generated. So could we all please thank Michele very much.